Good afternoon, good evening, or even good morning whenever you're watching this video. Today we're going to go over the chapter 3 notes, and chapter 3 notes are all about displaying and summarizing quantitative data. So the last ones we were looking at, okay, the last ones we were looking at were categorical data. And categorical data is like your yes or no type questions, your gender, your college major, right? Your questions that are all categorical data. This one is all about displaying and summarizing quantitative data. So it's different. Okay, we're not going to be using bar charts, we're using histograms that look very similar, but they don't deal with counts, they deal more with your averages and things, okay? Um, yeah, this is no pie charts. This one has some other stuff, so let's take a look, okay? So summarizing the data will help us when we look at large quantitative data. Without summaries of the data, it's hard to grasp what the data tells us. The best thing to do is to make a picture. We can't use bar charts or pie charts for quantitative data since those displays are for categorical variables. So histograms, the chapter example discusses earthquake magnitudes. First, let's at the entire span of the values covered by the quantitative variable with equal width piles called bins. The bins and counts in each bin give the distribution of quantitative variables. So when it talks about bins, okay, piles, I usually call them buckets, okay, but the bins, each one, think of that as like your own little like bar chart, okay? So one little piece there, okay, kind of like a bar chart, okay? So each one of these is a bin, and they're all equally spaced, okay? And you notice it looks a lot like a bar chart. The difference is this one, the bins, okay, these bars are next to each other. In a bar chart, if you remember, I was telling you, you can put them like that, but it's more suggested to have a space between it. The big reason is mainly, I think, to separate a bar chart from a histogram. They're different, okay? So a histogram plots the bin counts as the heights of bars, like a bar chart, displays the distribution at a glance. Here's a histogram of earthquake magnitudes. So off the bat, you see these lower ones in the 4s and 5s, okay, and even up here in the 9s, are less frequent than the ones between 6 and like 8, okay, where the ones in the 7s seem to take up the most space. Between 6 all the way up to 8 seems to be the majority of your data, with your middle probably being somewhere here around 7, okay? Here's a histogram of earthquake magnitude, okay, and over here obviously is the frequency, how often it appears, okay, so 50, 100, 150, and 200. You can see how often it occurs, okay? A relative frequency histogram displays a percentage of cases in each bin. Okay, remember relative frequency, that word is just simply percentage, okay? In this way, relative frequency histograms are faithful to the area principle, okay? So it's the same thing. These should look exactly the same, and we fill out with bar charts as well, okay? Relative frequency, okay? 4%, 8%, 12%, 16%. Kind of see that. I would say these ones are more common, but just know you can do the relative frequency as well. Okay. Here's a tech tip with a calculator for this class. While we are doing distance learning, we'll be doing a Google Sheet, a spreadsheet, and I'll set that up for you guys, and I'll go over that in our class meetings and post videos as well to help you guys out. Okay. Stem and leaf displays. Stem and leaf displays show the distribution of a quantitative variable like histograms do while preserving individual values. This is less frequent, but be sure you know how to do these. So this says, compare the histogram stem and leaf display for the pulse rates of 24 women at a health clinic. Which graphical display do you prefer? Okay, there's this display. This is there's 2 people responded between around 55 to 55, 60, 65, 70. Okay, this one goes from 55 to 59. This would then go from 60 to 64. This bar would go from 65 to 69, okay, 70 to 74, so on and so forth, okay. So this one says 88, that would be this guy over here, that little chunk right there. This says 80, 80, 80, 80, 84, and 84. So there's 1, 2, 3, 4, 5, 6 counts in this bin. So once again, that's 80, that's 80, that's 80, that's 80, and then 84, 84, so 6. So 80, 80, 80, 80, and 84, 84 should count up to 6 women responded with this. Okay, that was their pulse rate, sorry. There was 6 women with pulse rates between 80 and 84 there. And then there was 4 76s in this bin, 4 72s, 4 68s, those are in those bins, 60, and then 64, 64, 64, and then 56. Okay, it's just one way to organize your data. Okay, this is called a stem and leaf. Okay, so as this kind of says here, okay, when you do these, you can have, like, let's say it was 716, you'd put the 71, and these 6s, you always put the last number in the end. Okay, you can go higher than 99. This is called a dot plot. Okay, dot plots we don't really do in this class. Well, sorry, we don't really create these, but you'll be able to read them. They look a lot like histograms. They're just dots that are, okay, traditionally you do it left to right, but you can make it up and down. Okay. Think before you draw. Remember the make a picture rule. Now we have options for data displays. You need to think carefully about which type of data to make. So there's dot plots. There's stem and leaf. This one over here on the left would be a histogram. Okay. So before making a stem and leaf display, a histogram or a dot plot, check the quantitative data condition. The data are values of a quantitative variable whose units are known. Okay. Got to know the units, right? When describing a distribution, make sure to always tell about 3 things: shape, center, and spread. Shape, center, and spread. I would even put out there anything unusual. Okay. So for example, like this dot way up here is kind of unusual. You want to make a note of that. So shape, center, and spread. So shape. Does the histogram have a single central hump or several separated humps? For example, see that's got 2 humps. It has this data here and this data there. This has like, it's kind of uniform, but like one big hump in the middle. Okay, one big hump in the middle. Going back here to shape. Okay. Or is the hump on one side or the other, right? Is it like on the left side or the right side? Is it right in the middle? Okay, or is there like multiple bumps in it? Is the histogram symmetric or skewed? Symmetric means it looks like a bell. Okay, it's symmetric. Okay, maybe like a pyramid. Okay, it's like a triangle. It's symmetric. It's put a line in the middle and it looks like a mirror image of each other. Okay, skewed means is all the data kind of pushed to one side. Okay, think about like a right triangle. Okay, think about the right triangle like this or like that. Okay, is it all pushed to one side, going up, or is it all pushed to the other side? Okay. Any unusual features stick out? Okay, unusual. So when you think about the shape, again, like that, be kind of unusual. This one's kind of like skewed to, towards 150. This one seems to also be skewed towards 120. Okay. The humps. Does this histogram have a single central hump or several separated bumps? Humps in a histogram are called modes. Think about meaning a mode, right? Mode means what occurs most often. A histogram with one main peak is dubbed unimodal, okay? Like a unicycle. Uni meaning one. Histograms with 2 peaks are called bimodal, and histograms with 3 or more peaks are just called multimodal. So unimodal, bimodal, multimodal, okay? Those are very important to understand. So like this right here off the bat, bimodal. A bump, you see a bump, all right? Histogram that doesn't appear to have any mode and in which all the bars are approximately the same height. Remember, approximately, so it's kind of, it has a little bump right there, but overall, fairly straight. Doesn't look like, go back to the earthquake one. You see that's very obvious, it's a big bump in the middle. With this example, a lot more straight, okay? We call that uniform. There is no bump, there is no mode, there is no hump. We call it uniform. For example, we would expect a 6-sided die to produce a uniform distribution between 1 and 6. Okay, you take a die, You roll it, you get a number, okay, and you do that over and over and over and over and over again, something like that. With enough rolls, you would expect it to eventually kind of like equal out that you got ones, twos, threes, fours, fives, and sixes, equal amount of time or almost equal over a large sample of dice rolls. Okay. This is a symmetry. And I told you you can kind of cut it down the middle. If you fold it over in half, okay, roughly matches the other side. So it doesn't have to be perfect, but it has to be roughly symmetric. Like this right here, yeah, this bump here is kind of higher on this side, but it's pretty much the same on the left and right side. Okay. The usually thinner ends of distribution are called the tails. If one tail stretches out farther than the other, histogram is said to be skewed to the side of the longer tail. Okay. In the figure below, the histogram on the left is said to be skewed left, while the histogram on the right is said to be skewed right. So you notice how it has a tail on this side. Okay, that's like the longer tail. So it's skewed to the left. For this one, where the tail goes to the right, that's skewed to the right. Okay, or something like this one, right? Going back to the earthquake example, that one does not have a skew; it's more symmetric. Okay, but maybe you might want to mention it does look a little skewed to the left. Okay. About skews. So once again, it's talking about the shape. That's all talking about the shape. The shape of this would be skewed left. The shape of this would be unimodal, right? With no skew, it's just unimodal. This one would be unimodal but skewed left, unimodal but skewed right. Do any unusual features stick out? Sometimes it's the unusual features that tell us something interesting or exciting about the data. Okay, think about if you have like high school football players and how many touchdowns they score. Okay, and there's like a big bump in average of players and their touchdowns they score, and then one player, let's say, it stands out. Like, wow, that person had a lot of touchdowns or something that year. That's an unusual feature. You should always mention any stragglers or outliers that stand off away from the body of the distribution. Okay, outliers. We'll figure out if there's a way to actually calculate that. Besides just kind of eyeballing it and going, that looks like an outlier. Is it really mathematically an outlier? And we'll talk about how to calculate that this chapter. You should always mention any stragglers or outliers or any gaps. Okay, gaps in distribution. So something like this is a gap between this dot plot. Big gap there. You'd want to mention that when you're analyzing that when you're describing the picture. Right? And here's another example of a gap. Following histogram has outliers. There are 3 cities in the leftmost bar. So these would probably be outliers. Well, this is like the main data you would look at. Okay, it's unimodal, fairly symmetric. Okay, but it's got some outliers that a lot of times you might want to either not study, or maybe that's going to be the focus of your study. Like, why is this one over here? Where's the center of distribution? If you had to pick a single number to describe all the data, what would you pick? It's easy to find the center when a histogram is unimodal and symmetric. It's right in the middle. So talking about the earthquake one, like right in the middle. Okay. On the other hand, it's not so easy to find the center of a skewed histogram or histogram with more than one mode. So if it's bimodal or multimodal, very difficult to find the middle a lot of times. If it's skewed, let's look at these skewed ones. Is the middle one right here around 70 to 80? Or is it maybe more pushed to the left a little bit towards 65? Same with these charges. The middle's probably not here. The middle's probably a little bit over here, closer to about 200,000 or so. 150,000 maybe. All right. Let's talk about the median. Okay, center of distribution. The median is the value with exactly half the data values below it and half above it. It is the middle data value once the data values have been ordered. Okay, you put them from smallest to largest or largest to smallest, and the middle number is your median. It divides a histogram into 2 equal areas. If you find the median, in this case it was 7.0 for the earthquakes, that split it perfectly in half. Okay, it has the same units as the data. Okay, so make sure it's magnitude or feet per second or whatever your units are. We'll display that with not just the number but the units too. Okay, moving on. Variation matters. This is about variation of the values of the distribution tightly clustered around the center or more spread out. Okay, talk about the shape. We talked about the center, and now we're talking about how spread out the data is. Okay, but the values of the distribution tightly clustered once again, or is it more spread out? Always report a measure of spread along with a measure of center when describing a distribution numerically. Okay, think about the range. How do you find the range? You take your big number, take away your small number, and that gives you a range. So if in this case, go back to the earthquake example, you would take your highest number, subtract your biggest number, subtract your smallest number, and that would give you the value, okay, of how far it is from these two, the low point and high point. And that's kind of like your spread. Okay, once again, talking about the range, max minus min. Disadvantage of the range is that a single extreme value can make it very large and thus not data overall. If most of your data is here, like what the range is way over there, it doesn't really tell you a good story. Okay, but that's okay. It's still just more information. Here's what's called the IQR, the interquartile range. Let us ignore extreme data values and concentrate on the middle of the data. To find the IQR, we first need to know what quartiles are. IQR, we will talk a lot about this in the next couple chapters. IQR, the interquartile range. Okay? Essentially, it's the distance from your first quartile to your third quartile. And let's talk about quartiles, okay? Quartiles divide the data into 4 equal sections. Quartile, think about quarters. A basketball game or a football game, okay? Or quarters in your pocket, okay? 4 quarters make $1. 4 quarters in a football game, 4 quarters in a basketball game. Quarter means to cut it into 4 sections equally, okay? So, with your quartiles, if you chunk all your data equally into those 4 piles, so they're all the same, then take out your outer quartiles, what you get is all the middle of your data, okay? And a lot of times that middle data tells you a really good story about what's going on. So, IQR, once again, is your upper quartile. Take away your lower quartile, and it's kind of like the range, but it's a range, right? R, interquartile range. It's the range between those two values. Okay, upper quartile, lower quartile, subtract them, and gives you a better picture than the extreme numbers. It's the range of your middle numbers there, okay? It's a pretty cool concept. So, for example, the lower and upper quartiles of the 25th and 75th percentiles of the data, so the IQR contains the middle 50% of the values of the distribution. Best way to describe it, I'm thinking of, think about like a football game, and you don't care about the first quarter or the fourth quarter. You only care about the second and third quarters, and you add those up. Or basketball, same concept. Don't worry about the first quarter. Don't worry about the fourth quarter. Let's look at maybe like the points that were scored in the second and third quarter. That would be like your IQR. Okay, so get rid of the first part of your data, the last part of your data, and look at the 25th to 75th percentiles. Let's look at the middle chunk of your data. Okay. Something that you'll see a lot, okay, is called a 5-number summary. In the 5-number summary, it talks about 5 things, 5-number summary, okay? You usually start and end with your minimum and maximum, and then you do your quartiles. Okay, so minimum, quartile 1, quartile 2, which we just call median, because we think about like a football game or basketball game, again, after the second quarter, usually you have like a halftime, okay? That's your median. And then you go to your quartile 3 or third quartile, and then you go to your maximum, which is like the end of your fourth quartile, right? So min to your max, quartiles, and median, those 4 numbers. Okay? While you can count your way to a 5-number summary by hand for small data sets, we usually use technology to provide us with a summary. Usually, as it says here, a lot of problems will give you guys, and if you take the AP test, they'll just give you these numbers, okay? They'll just give you these numbers instead of having to take the time, because it might be a data set of 30 things, 70 things, 500 things, okay? It could be, a sample size of 1,000, and you can calculate it, but we're just going to give you the numbers, all right? Okay, so once again, 5-number summary, okay? A lot of times you might even hear it's just summary statistics, and a lot of times you just give them to you, okay? But probably for this chapter, we'll have you guys report this stuff. A box plot is a graphical display of the 5-number summary. So think about these 5 numbers and think about graphing those. actually not too bad, okay, if you think about it, okay? Useful for comparing groups. Box plots are particularly good at pointing out outliers, okay? And a lot of times what you'll see with box plots is you'll see them with a couple next to each other. So, it says step 1, draw a single vertical axis spanning the range of the data, okay? So you see the earthquake magnitudes, and we look at the important information. Going back to the data from earthquakes, I think this is the number of earthquakes. You see the bottom number is 3.7, so we can only go down to 3. That's cool. The top number is 9.1, so I guess go to like 9 or 10. And just make those little hash marks, make them all equal. They do that. They go actually from 4 to 9, and we're going to notice it's going to go above 9 a little bit and probably below 4 a little bit, and that's okay. But you're going to mark off, it says draw short horizontal lines at the lower and upper quartiles and at the median. So your 3 middle numbers. Okay? Think about these 3 middle numbers. 6.7, 7.2, and 7.6. So, what did I say? 6.7, 7.2, 7.6. So 6.7, 7.2, 7.6. 6.7, 7.2, 7.6. You draw little lines, make a big box around it, and that's your second quartile and third quartile, okay, like your second and third quarter. Then you draw your fences, okay? This is, you find your fences by doing your IQR, so this third quartile minus your first quartile, that's a number, okay? Take that number, multiply it by 1.5. Now add that number to your third quartile, and also take that number and subtract it from your first quartile. And that gives you these fences. Okay, one more time. Find your IQR, which is like your third quartile minus your first quartile. Take those numbers, multiply it by 1.5, then add it to the third quartile, subtract it from the first quartile, and that gives you what's called fences. Fences tell you what's the weird stuff, like what's your outliers. And then draw lines from the end of the box and down to the most extreme data values found in the fences. So you gotta, hopefully you have your data set, and you look at your biggest numbers that do not go beyond the fence, okay? Because beyond the fence is the outliers, and usually you graph those, plot those differently than just straight up draw them out, okay? Find your fences first, and then if you have numbers beyond those fences, you gotta try to ignore those for a short bit. Find the numbers that are below that or above that, depending on your fence, okay? And do not move beyond the fence, okay? If data values fall outside of one of those fences, we do not connect it with a whisker. So that's called a box, that's called a whisker, box and whisker plot, okay? Now, anything beyond that, okay, we often use a different symbol for far outliers, which are, so if you double that, if you have some crazy numbers, okay, you might want to look into doubling that fence range. If you have anything to see if that's called a far outlier, okay? So instead of being 1.5, double that to 3, right? And those will be your far outliers, okay? All right, moving on. So take a look at the histogram and then take a look at the box plot. You can see they kind of tell the same story different ways, okay? So this one kind of shows you that big chunk of data here in the middle. That shows you the big chunk of data in the middle. This one, it's hard to see the outliers though. You don't really know what's a true outlier, but the box and whisker plot does a great job at showing you outliers, okay? Summarizing systematic or symmetric distributions, the mean. So what this kind of talks about with symmetric data, if you have something that looks kind of like a bell curve, okay, if you have something that looks kind of like a bell curve, what you want to do is use your average. But if you don't have the, if it's not a bell curve, if you think there might be skews, right, skew left, skew right, or just anything different, you'll want to use the box and whisker plot, okay? You want to use things like the median, the quartiles, that helps you the most. When it's symmetric, so when it's like so if you graph this and it looks like a beautiful bell curve, okay, that's usually where we use the mean, okay? This is a fancy way to say add up all your values and divide by how many you have, okay? You're going to see this Greek letter a lot, like an E, that's called sigma, okay, that means to add things together. I believe this book and these notes we use a lot will say y. Oh, one thing we haven't talked about. You see over here it says y. You can use x, you can use y. This book decided to use y for their letter of your values. When you see this little bar on top, that's called y bar. So y bar equals your total divided by your n. N is pretty standard for your number of things you have. So think about an average once again. Line up all your stuff, divide by how many you have. That's what this says. So the sum of all of your values, add them all up, divided by how many you have. Okay? That will give you the average. Okay, the mean feels like the center because that's where the histogram will balance. The mean or median. Okay? Because the median considers only the order of values, it is resistant to values that are extraordinarily large or small. It simply notes that they are one of the big ones or small ones and ignores the distance from the center. Choose between the mean and median. Start by looking at the data. If the histogram is symmetric and there are no outliers, use the mean. However, if the histogram is skewed or it has outliers, you are better off with the median. So there's going to be a question for this chapter and maybe in the next couple chapters in this unit test. That'll be up in a few weeks. It'll ask you, here's a data set. Are you going to use the mean or the median? You're going to pick one, and there is a right answer. Okay, so if it's symmetric, okay, and there's no outliers, use the mean. Symmetric with no outliers, use the mean. Everything else, use the median. Okay, use the median, the quartiles, and that's the answer. Okay? So, talking about spread, when you're talking about the mean and symmetrical data, you should talk about the standard deviation. So the median, that's about the IQR and that kind of spread. But with the mean, its version of the IQR is what's called the standard deviation. Okay, and that helps you, as it says here, which takes into account how far each data value is from the mean. Okay, so it tells you how far it is from the average. If something has a small standard, if something is close to the mean, then it's like 0 standard deviations away from it. Okay, if it's far from the mean, it might be 1, 2, 3, 4 standard deviations away from the mean. Okay, the deviation is the distance that a data value is from the mean. Deviation, how far does it deviate? Okay, since adding all deviations together would total 0, we square each deviation and find an average of sorts for the deviations. Okay, so add all deviations together would total 0. We square each deviation and find an average of sorts for the deviations. If we do everything with technology, there's a way to do it by hand. It looks like this. This is called variance. You square root this, and that's your standard deviation. Okay. So variance is your standard deviation squared. It's by summing these squared deviations and almost averaging them. Okay. So standard deviation is just the letter S. Variance is S squared. Square root that, and you get the square root of that. Okay. So since statistics is about variation, spread is an important fundamental concept of statistics. Measures of spread help us talk about what we don't know. When the data values are tightly clustered around the center of the distribution, the IQR and standard deviation will be small. When the data values are scattered far from the center, the IQR and standard deviation will be large. So one more time. When the data values are scattered far apart, okay, the IQR and standard deviation will be large. Think about something maybe for height of high school boys, okay? There's probably not a big variance, maybe like from 5 foot to like, I don't know, high 6 feet, mid 6 feet, okay, about 1.5 feet. Not a large spread, okay, but maybe their weight, okay, you figure there might be some people that might weigh about 100 pounds, and some people might weigh up to like 300 pounds, okay? It's probably a much bigger spread data, much bigger standard deviation for weight than there might be for height, just because of the nature of the spread of data. Draw a picture. When telling about quantitative variables, start by making a histogram, dot plot, or a stem and leaf display and discuss the shape of the distribution. Next, always report the shape of the distribution along with its center and spread. So shape, center, and spread. If the shape is skewed, report the median and the IQR. If the shape is symmetric, report the mean and standard deviation and possibly the median IQR as well, if you want to give that your time up for that. One more time, if it's skewed, report the median and IQR. Okay, skewed means it's got that weird shape to it. Okay, like a right triangle. But if it looks more like a bell, then we use the mean and standard deviation. Okay, so make sure you know the difference between the two. Any unusual features, okay, if it's got multiple modes to it. Oh, and also, yeah, the whole idea of clear outliers. So if you can calculate them mathematically, great. But if it's nothing's clear, then don't worry about it. Okay. What can go wrong? Don't make a histogram of categorical variables. Bar charts and pie charts are fine. Don't look for shape, center, and spread of a bar chart. Okay. I mean, you can, but we're not going to right now. Don't use bars in every display. Save them for histograms and bar charts. Below is a badly drawn plot and the proper histogram for the number of juvenile bald eagles cited in a collection of weeks. So weeks, week 2, week 4, week 6, week 8, week 10, week 12. Okay, number of juveniles cited. Juveniles cited over the number of weeks. Which one looks better? I think this one's better, but kind of fun. Yikes. Okay, this actually looks a lot better. Next to the number. I like the weeks on the bottom, but whatever. It is better to have it that way. But yeah, don't have your thing centered like that. You want it to the right. That way it's clear. Okay, so choose a bin width appropriate to the data. Changing the bin width changes the appearance of the history. Making smaller bin widths like this, putting bigger sums of data makes it look like that. Which one looks better? One actually doesn't look too bad. Okay. I mean, this one they tell kind of similar stories, but yeah. Okay. It's appropriate for the data. Don't forget to do a reality check. Don't let the calculator do the thinking for you. Make sure you know what you are doing with the spreadsheets or calculator. Okay. Don't forget to sort the values before finding the median. Don't just count your numbers. Okay. Make sure they are in order. Don't worry about small differences when using different methods. Don't complete numerical summaries of categorical variables. Remember, it's quantitative variables we're doing right now. Don't report too many decimal places. It depends on the problem. 1, 2, 3, 4 can be appropriate. Don't round in the middle of the calculation. Just wait till the end to round. Watch out for multiple modes. Okay, unimodal, bimodal, multimodal. Beware of outliers and make a picture. Okay. So, a lot of stuff going on. It was a pretty heavy chapter, okay? But just know that this is quantitative data. We have histograms, dot plots, etc. Box and whisker plots. Box and whisker plots are for when you're using the median and the quartiles, okay? Think about the IQR, the ranges. And then if you have the beautiful unimodal bell-shaped data, that's where the median, the mean means the average and standard deviation shine. Okay, it doesn't look like a bell-shaped curve. Okay, if it's not bell-shaped, looks like it's skewed one way or the other. That's where you want to use the median. That's where you want to use the IQR. Figure out like your boundaries. If you look at your quartiles, that's going to be the best display for data that's not symmetrical. Okay. All right. We'll see you guys in class this week, and let's keep knocking this stuff out. All right. Have a good day. Bye.